Starting with the presentation of Anja Borschen about experiments done in DHI.
Thank you, Mr. Chairman. Ladies and gentlemen, I would like to welcome you to my presentation. I would like to present our Cornerdike-Project. It was about wave run-up and wave overtopping under very oblique wave attack. And first of all, I would like to introduce our project group. The project leader was Technische Universität Dresden, and then we had colleagues from the Aachen University, Professor Schüttrumpf and his colleagues. From these first two universities are from Germany. We had colleagues from Ghent University from Belgium, Professor Troch and his colleagues, and from the Brno University of Technology from the Czech Republic, and last but not least, Vandermeer Consulting from the Netherlands. And the test facility we used was the Danish Hydraulic Institute, the shallow water basin there. I would like to give you a short overview about the objectives of our project, the model setup, and some preliminary results, and of course a short conclusion. So we investigated wave run-up and wave overtopping, and you can see in these two sketches here which parameters influence wave run-up and wave overtopping. Of course, these wave characteristics are important, wave height and wavelengths and so on. And on the other hand, the dike characteristics or the characteristics of the structure. In our case, it was a sloped dike, and here mainly the slope angle and the freeboard height. But very important parameter is the obliqueness of the waves. So we had investigated oblique wave attack, and we also looked into the difference between longshore waves and long crested waves and short crested waves. As you can see here, long crested waves have mainly one wave direction, and for short crested waves we have spreading around this main wave direction, and this is described by the spreading parameter sigma. And the angle of wave attack is defined according to the perpendicular wave attack. We call it beta, and for perpendicular wave attack we have beta equal to 0. And to investigate very oblique wave attack, we had to introduce a corner in our dike line or shoreline, and if you do so, you could expect, of course, some diffraction effects, and we have to be careful about that too. As you can see here in the lower picture, waves come around this corner and will run up here too, although the angle of wave attack is greater than 90 degrees. And if we introduce a corner, of course, we have to look at this energy concentration at the corner, and we would expect a higher run-up at the convex shaped coastline, of course. So here are the main formulas we used for the wave run-up. It's from the Overtopping manual from 2007. The first formula is for braking waves, and second is for non-braking waves. And you can see here these parameters which are describe some behavior of the waves and the characteristics of the structure. We use for run-up the wave run-up height, which is exceeded by 2% of the incoming waves. And as you see in the first formula, our influence parameter with, which describes the influence of oblique wave attack is a factor of, in the formula, so we can determine this factor if we calculate the ratio of the run-up height in case of oblique wave attack to the run-up height in case of perpendicular wave attack. The other influence parameters were not considered. We had no berm or no roughness elements on our slope. So this is the formula for the overtopping. First one is for braking waves, second one for non-braking waves. You can see some more parameters which are influence this calculation, and our influence parameter gamma beta is here in this exponential coefficient, so we have to calculate the ratio of this coefficient if we would like to calculate gamma beta. So what is the state of the art about the influence factor gamma beta? If we have an oblique wave approach, the run-up and the overtopping decreases, so we expect values lower than 1. You can see here in this diagram the angle of wave approach and the influence factor beta on the y-axis. And we have different empirical formulas for short crested waves. It's the black line. For long crested waves, these are the blue lines, and for long and short crested waves are the green lines. So there are formulas for both wave types. The question is there a difference between short and long crested waves? This formula for short crested waves is that, but we cannot distinguish already. So you see that there is a quite of data set in this area, but we are focused on very oblique wave approach beyond an angle of wave approach of 19 degrees. And this was our investigation area. What was our time schedule? We did the test at the DHI in September and October 2012. We had 2 weeks for the general model setup, for instrumentation, for overtopping tests and calibration. Then we did our wave overtopping tests in 1.5 weeks. After that, we changed the instrumentation for the run-up test, to prepare for the run-up tests, and had 1 week for all wave run-up tests. We ended up with about 93 wave overtopping tests and 65 wave run-up tests. This is our general model setup in the shallow water basin. This shallow water basin is 35 meters long, 25 meters wide, and you can see here our dike, and we introduced or we built a dike with 2 legs, and these 2 legs were joined with a corner, so that's why idle corner dike. And these 2 legs of the dike had an angle of 19 degrees to each other, and the whole structure was shifted a little bit so that there is an angle between this P dike and the wave generator of 50 degrees. And at this left side here you can see the wave generator from the DHI, which is 22 meters long. Of course, we measured the wave field. You can see here some wave gauges at the dike toe, and this is, of course, to determine the incoming waves. And the first test were about overtopping. So here you can see our corner dike with 5 overtopping units, 2 at the P dike and 3 at the N dike. And these overtopping units contained of an inner tank. It collects the incoming water. This was measured by a weighting cell, and this inner tank and the weighting cell was put into an outer box to prevent them from getting wet. And these inflow channels connect the dike crest and to this inner tank, and we had differences in the width of the incoming channel. So here at the P dike it was 10 centimeters wide, and at the N dike it was 30 centimeters wide, because we expected more overtopping at this area as at the N dike. And at each inflow channel, the flow characteristics were measured with these small wave gauges, and So this was done for all devices and for all investigated angles of wave attack, and you can see here the upper table is for the run-up tests, and this is for the overtopping test, and you can see quite, recognize a pattern here for tests. Yeah, we had to compare our results, of course, to former investigations. This is an example for the overtopping. The black line is the Eurotop manual formula, and our tests here are the reference tests with perpendicular wave attack for long and short crested waves, and it fitted quite well. We could distinguish an effect of oblique of this directional spreading on the wave overtopping, as you can see here in this green line. These are the test results from the Cornerdike, and it confirms the test results from Kortenhaus et al. From 2006 very well, and we could also confirm this this formula for our tests considering wave run up on the cone here. For the wave run up of the for the reference tests for wave run up for long crested waves and short crested waves, we have quite different results. For short crested wave, we can confirm the known formula quite well, and for long crested wave, we have a very distinguished effect of this wave energy concentration at the corner. And for the P-dike, we had quite too small values of run-up, but this is mostly due to the diffraction effects. And this is a picture with quite a lot of dots and crosses in it. This is all the tests for wave run-up and wave overtopping. On the x-axis is our angle of wave approach, and on the y-axis our influence factor, and we have this decreasing trend as we had expected. We have quite good agreement here in this middle area between angles of wave approach of 40 to 80 degrees, but then we have different trends. For overtopping, this is still decreasing, but for run-up, we have an increasing of the run-up height. So we discuss this effect. We think it's it's caused by redirection of waves around the corner here that prevent waves from running up at the lee shore, and maybe in this case for very oblique wave attack, this effect is not so strong. And I would like to show you also some results concerning this lee shore here. We have this camera results from camera 3. This is the circle. For camera 4, it's the square, and camera 5, we have this cross. And for short crested waves, it is like we would expect that the run up in a greater distance from the corner is smaller than the run up here at the corner itself. But for the short, long crested waves, we have a quite different effect. We have an increase in the run up and reach quite this run up here for perpendicular wave attack. So I would like to say very short something about our outcome. We have a wide data set created of wave run up and wave overtopping under very oblique wave approach, and we are still discuss this, but we think we are able to extend these empirical formulas for the influence factor gamma beta. We were quite delighted that we had so much young researchers in our research group, and several graduation works were done within it. But of course, for the future, we would like to verify our test results and maybe consider a longer dike line from that corner to distinguish a point where this diffraction effects are at its lowest. So last but not least, I would like to thank all my colleagues from our project group and the DHI staff for their excellent work, and I would like to thank you for your attention.
Thank you, Angie. Is there any question, please? Mark?
I'm a bit worried about the quality of your data because of that diffraction area that you have shown in one of your slides. Was it possible to use a corner reflection method to have a wider area in your basin with the right wave conditions?
This diffraction area was quite distinguishable for long crested wave. For short crested waves, it was an assumption by our group that we have a diffraction area of about 50 degrees. So for long crested wave, it was confirmed. So we had to a very certain degree a lower influence by diffraction. But you are right. We had to exclude these data.
Yes, but it is not so easy to see if you have short crested waves, but it is still there. So I'm really quite worried about the quality of your data.
Okay. Yeah. Okay.
Okay, thanks. Is there any other question?
Yeah, I'm over good, Mr. My question relates to how you handle the varying water level, the storm surge level. I presume you keep the water level constant in your tests.
For the run-up test, we had only one water level of 70 centimeters, but for the overtopping tests, we had tests with different water levels, so different freeboard heights.
Okay, thank you very much. We'll stop here and we'll go for the next presentation. Thanks.